Hello and welcome to the 19th session of the discussion on machining science course. Now, in our previous session, we were discussing the economics of machining, and we said that the aim of any production is to produce the final part with the accuracy, size, finish along with the minimum cost. So, therefore, we have to look into the process parameters by selecting which we can actually get the minimum cost. Now, there are three criteria. We said that minimum production cost criteria, maximum production rate criteria and maximum profit rate criteria. By this we mean that for any machining, any set of machining parameters, we will always get a minimum cost or maximum production rate or maximum profit rate. So, the idea is for each of these criteria we have to find out these parameters which will be optimum at which these are satisfied. Let us say first the minimum production cost criteria, which we started looking into the last class. So, in which we have to find out all the costs involved in the process in the machining of that a particular part, and then we have to minimize that cost. That is the basic idea here. So, therefore, for any material, any part, cost per piece will be consisting of 5 costs. We said that material cost, then the setup and idle time cost per piece, machining cost per piece, then the tool changing cost per piece and the tool cost per piece. Now, the material cost does not depend on the cutting conditions, because we are particularly looking into the cutting condition, and in this particular case we said that for simplicity we will look into the cutting velocity. Okay. So, we will find out the optimum value of the cutting velocity at which particularly this criteria, that is the minimum production cost criteria, can be satisfied. Now, the setup and idle time cost, this also remains independent of cutting conditions, either cutting velocity or feed or depth of cut, and this can be defined as the time taken for settling and the ideal time into the lambda 1, which will be the overall overhead plus the labor cost. Now, the machining cost will be the machining time Tm, and that has to be multiplied by the cost that we are incurring for that time, that is the lambda 1, which is overhead plus the labor cost per piece. Now, the Tm, we know that this is L by Fn, and n can be substituted because pi dn is equal to velocity. So, this can be substituted by the velocity, and it will be lambda 1 pi dl divided by 1000 Vf. 1000 we have taken to convert meter into millimeter, and the so that the unit finally could be in rupees. Okay. Now, here it is shown that the Tm is equal to L by Fn, which is pi dl by 1000 F into V. Now, the tool changing cost R4, this is equal to the number of times we are changing the tool into how much time it is taken each time, that has to be multiplied by the lambda 1, which is overhead plus labor cost. So, number of times we are changing the tool can be given by the Tm, that is the machining time, and if we divide that by the tool life is T. Now, from the tool life equation we know that Vt to the power n is equal to C constant, and C can be taken as k to the power n. Now, from here we can find out that the tool life is equal to k, some constant, divided by V to the power 1 by n. V is the cutting velocity. Now, therefore, R4, that can be equal to, if we put the value of t here, which is k by V to the power 1 by n, it will be this expression. So, this expression we have taken only here we will be considering the cutting velocity V. Now, the tool cost per piece, again we have to calculate how many times we are changing the tool, and that has to be multiplied by the tool cost per piece, which is lambda 2. Here you have to be careful that lambda 1 will not be involved, because here it is the tool cost which we are incurring, the number of times we are changing the tool, and that has to be multiplied by the tool cost per piece. So, therefore, T m by T, T we have found out earlier, T m we found out earlier, that is the pi d L by 1000 V f. Value of T we found out as k divided by V to the power 1 by n. So, here it will be V to the power 1 by n by k, and that has to be multiplied by the tool cost per piece. Now, the variable at our disposal, as we said, that we are considering the cutting velocity. That means, for the cutting velocity we will try to find out the optimum value for which the cost will be minimum. So, therefore, the function that we will be having, that is the R cost per piece, that will be a function of the velocity, let us say. That is equal to R 1, which is independent of the cutting velocity, R 2, which is independent of the cutting velocity, which is given by delta lambda 1 into T s, R 3, this is the machining time that we have already calculated, R 4, this is the tool changing time cost per piece, and the tool cost per piece. So, all these we found out, we sum them together, and we say that this is a function of the velocity, cutting velocity, which is basically the cost per piece. So, therefore, we will segregate the V in terms of V to the power minus 1, V to the power 1 by n minus 1, and so on. Then V will be V optimum, that is the optimum velocity to get the optimum velocity of the cutting velocity, optimum cutting velocity. We will take the first derivative of this equation, or the tool cost per piece, cost per piece equal to 0. So, if we take the derivation, first derivative of this equation, or first derivative of the df divided by with respect to cutting velocity, we will get this. Okay. V to the power minus 1 we have. So, it will be minus, this terms will be will not stay, because it is with respect to cutting velocity, and R 1 and R 2 they do not depend on the cutting velocity. So, they are going out. Now, this term will be minus lambda 1 pi d L by 1000 f is constant, because it is not dependent on the cutting velocity. So, cutting velocity is here. So, it will be V to the power minus 1, minus will be here, and V to the power minus 2. So, it is the derivation of this. Similarly, the derivation of this will be 1 by n minus 1 coming out here, in this case V to the power 1 by n minus 2, and here also it will be the similar one. So, here it is the del lambda 2, which is the tool cost per piece, and here in these two factors it will be lambda 1, which is the overhead plus labor cost. So, then if we rearrange them and make them equal to 0, in this case all the V velocity that we will be getting here, those all are the optimum velocities, because we have taken the first derivative of this equation and we are equalizing to 0. Therefore, we will write V optimum in all those cases, we will reorganize them, and since it is equal to 0. So, these terms will be cancelled, and we are getting minus lambda 1 from here, plus and we are getting the common of the V to the V optimum to the power minus 2 and this factor. So, this will be now remaining will be 1 by n minus 1 V to the power 1 by n, and this will be V optimum of course, and similarly this factor. Here it will be also V optimum to the power 1 by n, because we have taken V optimum to the power minus 2 and pi d L by 1000 f common. So, this is equal to 0, and if we solve that equation, we will find that the V optimum is equal to k n lambda 1 divided by 1 minus n lambda 1 t c t plus lambda 2 to the power n. Here of course, the k is constant, n is constant, and those constants are coming from the tool life equation, Taylor's tool life equation. These constants will depend on the combination of the tool and the workpiece material of course. So, therefore, this is the minimum cost criteria, and as per minimum cost criteria, this is the value of the optimum value of the cutting velocity if we can machine with this cutting velocity, then we will be getting the optimum cost, and how to get this V optimum, that we already found out here. So, now if we plot the curve in y axis, if you put the cost, okay, total cost per piece, and here you put in the along the x axis we will put the cutting speed, that is the V velocity. So, in that case the material cost will be constant, it does not depend on the cutting velocity, it will incur a certain cost which will be constant. It does not matter how much speed it is there along the speed. Settling plus ideal time cost, which is R2, that also remains constant along the cutting speed, meaning as the cutting speed is increasing, there is no effect on the material cost or the settling plus idle time cost. Once again, please correct it that this is not ideal, but this is idle, E-I-D-L-E, idle time, when it is stopped, when it is not working, idle. So, these two costs will be remaining constant. Then the machining cost, and if you see the equation of the machining cost, it will be a nonlinear equation, okay, because we have seen that the machining cost will be R3, this is lambda 1 pi d L divided by 1000 F into V to the power minus 1. So, this is the nonlinear equation, it is varying in this way. Okay. As the cutting speed is increasing, the machining cost will be reduced. And next is the R4, which is the tool changing time cost per piece, and then this also will be a nonlinear equation, and the tool cost, which is also a nonlinear equation. All these three, tool cost, tool changing cost and the machining cost. And if we draw that, the total cost, that is the sum of all of them, it will be a curve like this. Okay. This is the total cost profile, and in here there will be a minimum, and this minima indicates that this is the point where we will have the V optimum. This is the value of the V optimum, and at this V optimum value, the cost that we will have is minimum, in the sense that if we reduce this value of V, cost will be higher, or at a higher velocity than the optimum velocity, the cost will be again higher. Only at this value of the velocity, which is equal to this, we will have the minimum cost. So, this is what we mean by the minimum cost criteria, and this is the optimum velocity by which we can get the minimum cost. Mind one thing, that here we are taking care of only the velocity as component. Now, similarly, we can also find out the optimum value of the feed and the optimum value of the depth of cut, at which the cost will be minimum. In that case, as you understand that the first derivative has to be taken with respect to f feed or with respect to depth of cut and equal to 0. In that case, the value of the f that we will be getting, or d, that is the depth of cut that we will be getting, will be the optimum value. So, here we have neglected that, we have taken only the optimum velocity, and similarly you can also get the optimum value of the feed and the depth of cut. Let us see the next criteria, which is the maximum production rate criteria. That means, here also we will take only the velocity component, and we will see what will be the value of the optimum velocity at which the production rate can be maximum. Now, to have the production rate maximum, you know that the time taken to make that part or produce that part should be minimum. Okay. So, therefore, the idea is that we will sum up all the times which are taken for making that part, fabricating that part, and we will minimize that time, so that the production rate could be maximum. So, let us do that. Now, the maximum production rate can be achieved if the total time required per piece is reduced to minimum. Now, total time taken to produce the part, fabricate the part, is equal to the settling and idle time per piece plus machining time per piece plus tool changing time per piece. These are the three components of times which are involved in the total time. So, the settling time is Ts, machining time we said is the Tm, and the tool changing time is Tct. That has to be multiplied by the number of times we are changing the tool, because this is all this is the machining time per piece, this is the tool changing time per piece. Okay. Now, Tm we have taken as machining time per piece, but TCT we said the tool changing time, and tool changing time per piece will be tool changing time into the number of times we are changing the tool, and which as we have seen that will be Tm machining time divided by tool life. So, we have said earlier that Tm can be found out by this way, that this is equal to pi dl by 1000 V into F, and TCT into Tm by T can be written as this. This also we have seen earlier. Now, for optimum speed, therefore, this equation, that is the T total time that is taken, if we take the first derivative of that and we equalize to 0, that will give us the optimum velocity with respect to velocity, cutting velocity. So, dt by dv, that will be equal to, this is not being considered because this does not depend again on the cutting velocity. So, these are the two components. Here it will be v to the power minus 1, and we have seen earlier that this will be the result of the derivation of this component, and the derivation of this component will give you this. So, therefore, if we now solve this equation, make it equal to 0, like in the case of the minimum cost criteria, we will get the optimum velocity, which will be k n divided by 1 minus n into T c t to the power n. Now, this is also a value which is optimum value of the velocity, but at this value we will be getting the production rate maximum, but not the minimum cost. Okay. For minimum cost anyway we have to get into the minimum cost criteria, and with this value we will get the minimum cost. Okay. So, this we have to keep in mind that for each criteria the value of the optimum parameters are unique, in the sense that for with this value of V optimum we cannot satisfy the other criteria like maximum profit rate or minimum production cost. Okay. Now, similarly, for the maximum profit rate criteria, we can rewrite this equation as profit rate. This will be S minus R divided by T. Now, S is the amount received per piece excluding material cost and the cost per piece, meaning that we have fabricated a part or a unit, and for how much money we are selling that is in one word it is a selling price, minus cost per piece, how much we have incurred to produce that part, and divided by the total time per piece which has been taken. Now, then the R we have found out. Okay. This is the total, this is the cost per piece. We found out the total time per piece, and let us say S is constant for the simplicity, meaning that selling price is not fluctuating, and for the constant S, knowing the R which we have derived earlier and knowing the value of the T which also we have derived earlier, we take the first derivative of this equation and equalize to 0, we will get the value of the V optimum. Again, with this value of the V optimum we cannot satisfy the other two criteria, but it will be unique for this criteria, that is for maximum profit rate. Now, once we got these values of V optimum, it is not necessarily that we would be able to use these values. There are certain restrictions, in the sense that there are certain maximum power restriction, speed restriction, force and vibration restriction, surface finish restriction. Just to give you an example, that maximum power restriction, power can be calculated by this, that is constant Bw, V is velocity, feed and the depth of cut, the Bw m1 m2 constant. Now, if we say that the power required for the machining is something P, let us say, or Pw, and the according to the optimum velocity or whatever, whichever criteria it is, we are getting the power which will be more, then we have to reduce that value of the optimum velocity to get within this power, meaning this power is the one, this is the value by which is required to fabricate that part, to make that part, and we cannot have the power consumed by the fabrication less than the power given in the motor or given in the machine. So, this is the machine power. Okay. Machine will be designed with this power, and the power we can calculate required for the fabrication by the optimum velocity that we have calculated from the economics of machining. And if that power calculated from the economics of machining is more, we have to reduce the value or decrease the value of the V, so to get the decreased power to match with the power of the machine available. This is the maximum power restriction. Similarly, we will have the speed restriction, because most of the machine tools will have the maximum speed and the minimum speed. Maximum speed, you cannot go beyond maximum speed, because this is not allowed by the machine. Minimum speed is limited by the let us say built up edge formation, and if the V optimum that you calculated, if that is more than this, more than the V maximum, then you have to reduce it. If it is less than V minimum, you have to increase that. So, you have to adjust these values to get the right kind of fabrication. Similarly, we have a force and vibration restriction. Machine components are designed for a maximum permissible load, beyond which the tool work deflection will be excessive. So, you find out the cutting force by this formula, cutting force which will be designed according to the machine, and if this is coming out to be more or less by the optimum velocity that you have calculated, you have to adjust it. That is the basic idea behind the adjustment. And finally, we have the surface finish criteria. Surface finish criteria says that the surface finish overall should be less than this value. Okay. And if by putting the V optimum calculated earlier from the economics, if you see that this equation is not satisfied, you have to adjust the V optimum to satisfy this equation, that the HM, that is the surface roughness, should be less than or equal to the constant Bs feed to the power some power which is constant, and V to the power A2 which is some constant. Okay. So, this is what we mean by the restrictions on the cutting components, and whatever you have calculated from the economics of machining, they have to be adjusted to certain extent, so that these criteria are satisfied. Okay. Here whatever I said, these are written here, so you can read them, all right. Now, let us talk in brief the thermal aspects of machining, and here I will particularly discuss the sources of heat generation, how the heat is distributed, and how to measure the temperature in the shear zone, because this is very difficult to measure. When you measure the temperature with the thermocouple, for example, okay, you will measure the temperature in the cutting zone, but you cannot individually measure the cutting temperature in the shear zone or the cutting temperature in the chip tool contact length, for example. So, you have to analytically find out through a model how to calculate that temperature. Well, first of all, let us say from this diagram, we know that we have already discussed this, most of the heat is generated because of the because of the plastic deformation, which happens in the shear zone. So, 80 to 85% heat is generated because of this. Next, it is because of the friction that the chip is moving along the rake face. So, here about 15 to 20% heat is generated, and finally, we have the rubbing of the flank face with the already machined surface, and the contribution of this friction is about 1 to 3%, not more than that. Okay. Now, the heat sources therefore are the shear zone, heat generated due to plastic deformation of the work material, the chip tool interface, as I said, that heat generated due to frictional rubbing between the rake face of the tool and the chip, and finally, the work tool interface, that is heat generated due to frictional rubbing between the flank face of the tool and the workpiece. So, once again the major contribution is by the plastic deformation which occurs in the shear zone. Next is the chip tool contact area. Here about 15 to 20% heat is generated and 1 to 3% heat is generated due to the rubbing of the flank face with the machined surface. Now, earlier also we have discussed that when the cutting speed is increasing, then cutting velocity or cutting speed increases, then the temperature increases non-linearly. Okay. So, theta is proportional to root over V c. So, therefore, when the cutting speed is increasing, the heat increases. This is along the y axis, we have the percent of total heat generated due to the machining. Okay. So, total heat, meaning that this is due to plastic deformation, due to the friction between the chip and the rake face of the tool, and this in this zone, that is the flank face and the machined surface. So, total heat 100% is here, and out of the total heat, the heat carried by the chip is maximum. So, most of the heat is carried out by the chip. So, this is also about, you can say roughly about 80% of the chip, 80% of the heat is carried away by the chip. Now, about 15% is carried away by the goes to the tool, and the rest goes to the workpiece. So, as you understand that during the machining, therefore, the chip will be the hottest, next to that will be the tool, and next to that will be the workpiece. Okay. This coming to the tool, the chip, from the chip, because the chip is hottest. See, what happens here is the chip is getting heated up because of the plastic deformation in this zone. So, after it is heating up and maximum heat is generated here, the hot chip will be further heated up by the friction between the chip and the rake face of the tool. All right. So, therefore, this is the phenomena which actually you have to understand that how the temperature occurs. All right. Next, let us see how the average shear plane temperature can be found out. So, this is a model, thermal model, by which we can estimate the we can analytically find out what is the temperature occurring in at the shear plane. Okay. Now, the average temperature at the shear plane can be estimated from the rate at which the shear energy is expended along the shear plane. So, we are applying the shear force, we are applying the shear stress, and that shear energy is expended along the shear plane. Okay. So, along the shear plane where the maximum heat is generated, and we are here trying to find out the heat generated in the shear zone particularly. Okay. So, here the shear energy is equal to the Fs into Vs. So, we found out earlier that the specific energy is equal to the product of the velocity and the speed. Same thing here, this is the shear energy. So, the shear energy will be the product of the shear force and the shear velocity therefore. So, you mind one thing, that shear force will be acting along the shear plane of the machining. Okay. So, shear plane is here, and the Fs, if we remember, we have done that in the Marchand circle diagram, that the Fs is parallel to the shear plane, and this is acting along the shear plane. So, this for orthogonal cutting due to transportation, the heat flow equation, or this equation can be written that rho T1 B C V W into theta s prime or theta s bar minus theta 0 is equal to beta into W s, which is equal to beta into F s V s. Let us see what is it. Now, we are saying that we are considering the orthogonal cutting, and in orthogonal cutting we will find out how the temperature is produced. Now, the temperature is produced because of the transportation, due to transportation, and due to transportation, this is the formula that is well known in the thermal engineering, that the density into the T1 is the uncut, this is the uncut thickness, we have always taken that. The B, this is the here it is written width of workpiece. Okay. C is the specific heat, VW is the work velocity, theta S bar is the temperature which we are interested in, that is the temperature which is generated in the shear plane. The theta 0, this is the ambient temperature. Okay. Now, this from this equation, well, here what we are saying is that this heat that is generated, this is equal to the beta, which is the fraction of heat which is going to the chip, which is about 0.8. As I said that about 80% of the heat goes into the chip. All right. So, therefore, this is the fraction of heat going to the chip, which is 0.8, and the Ws, as we said, the Ws is the shear energy which is being expended. So, once again, for orthogonal cutting due to transportation, this is the equation that we know from the thermal engineering, and this is the heat which is generated here by this equation, which goes fraction of heat going to the chip will be 0.8 into the shear energy which is expended. So, Ws equal to Fs into Vs. So, we can substitute this. Now, here therefore, from this equation we can find out that theta S bar, which is the temperature which is occurring in the shear plane, which will be equal to the 0.8, which is the beta we have taken, there is a fraction of heat going into the chip, Fs into Vs divided by the density, uncut thickness, width, this is the specific heat and the velocity of the workpiece. Okay. So, this will be plus ambient temperature, whatever will be the ambient temperature. Now, Fs we know from the merchants that Fs is equal to Fp cos phi minus Fq sin phi. If you remember, in the merchant circle diagram we have said that Fs is equal to through the Fc and the Ft. So, this is equivalent to Fc and this is equivalent to Ft. So, Vs also we found out from the sine rule, if you remember, and then we put this value of the Vs and the Fs, we find out that this is the final equation of the heat generated in the, or this is the average shear plane temperature. This is the only way to find out the average temperature in the shear plane analytically, because we cannot measure, as I said earlier. Rest of the things we will discuss in the next session. Thank you for your attention.